Okay, cool. Well, thanks everyone for coming and to talk about cost models. So I'm Stefan. I've been leading like the cost model effort in XLA GPU. And I would like to have this, as interactive as we can make it. So in particular, I think I would like to start with like collecting agenda items if there's things you want to talk about, so that we kind of have them to start with. And then I have a couple of slides to kind of talk, give an overview what I think, why cost models, where we use them, and what we're going to do on the XLA GPU side. But from my perspective, I'm really interested to understand like, other use cases and thoughts other people have, right? If that makes sense. So do we have any agenda items, any things people want to bring up? I will just walk to the whiteboard.
I was just curious, like what the scope is. For example, I also going to consider, I guess, layouts for certain kernels. You need to switch from one file into the other one. And depending on that, like you might have different choice of kernels. Like, it would be nice to figure out what the scope of project will be.
So one question is, what's the scope? We also want layouts. Any other suggestions?
Heterogeneous devices. I will just write this and I can read it so you won't see whether I misspelled it.
I actually wonder if this is similar to like just graph partitioning, because both devices and different users, different libraries. So
yeah, that's a good one.
Yeah, and the communication interface.
Actually, what are the things we want to try based on these cost models? Is it mostly fusion, building, are there other things?
and also, is it analytical or is profile based?
That's also a good question. All good for that.
I'd like to understand how cost modeling with Triton backend works as well. Is that something that's in the plans?
With Triton? Is that what you said?
Yeah, with the OpenAI Triton backend in XLA.
Yeah, also a good question. Anything else from the online attendees?
So how are we planning to gather the data for the cost model? Or will there be hooks, or like how exactly will the framework know about it?
So what does that mean? So how the cost model is being used, how it's integrated, or what does it mean? How does the framework know about it?
So the data for like, we'll need to build the cost model, we'll need to have some data which will generate the cost model. So is it going to be on the fly based on that current model, or are we going to profile things over a period of time?
So you're thinking of like a learned cost model in essence.
That's right. Yeah.
Yeah.
I guess let's add one more: extensibility for custom ops or third parties.
Yeah, that's also good.
Maybe traceability as well. If you're targeting new hardware.
Okay. Maybe also like portability.
Yeah.
Yeah, it's also like generality, I guess. Yeah, so makes sense. More agenda items.
Is offline versus online included already in profile based versus kind of implicit, but maybe?
Yeah, I think that's like
I think we can list everything and then kind of group things that are similar.
Yeah. Okay. Yeah, interesting. I think we can naturally kind of figure out. So I think this for me looks mostly like the scope of cost modeling and the use cases. And interestingly, the second round of questions were all about how, right? So analytical, profile based, how to do Triton, how to learn one, how to make it extensible. So I think that seems like if I had to group this, that's the two themes. So maybe let's group it in that way, right? Makes sense. And also that essentially, so I have some presentation for this part, so what we're doing, just briefly, so people have an idea. And I don't want to talk too long about it. Maybe that's a good segue, and then we can talk about how to actually get to cost models. Okay, that sounds like slides. So we did the agenda building. Yeah, so the question I anticipated that would come like this, why cost models, where to use cost models. And I can mostly talk about where we're using them at XLA GPU today. There's like two main use areas. One is the latency hiding, right? That's also there, like communication primitives. And if you've watched OpenXLA presentations, you likely have seen the picture on the right a couple of times. But that's the basic problem, right? So you have some communication primitives, and then you have some computation. And what you want to do is you want to run computation while you're doing communication, right? So you want to fill essentially the gaps while you're waiting for data to arrive. But to do that efficiently, you have to understand how long your computation takes, because you don't want to overfill the gaps, because then you might run out of computation to fill other gaps, right? So you want to have this as optimal as possible, or as needed at least. And for that, you need a cost model, right? So, or something, right? You can also do this profile based or something, but you need a way to predict the cost of the communications and the cost of the computations, so that you can kind of derive this schedule. So that's one of the areas where we're using this. And the other areas is like fusion decisions, right? So that's the second key area. And right, the slide says why we do fusions. I think we all know in the room why we do fusions, so we don't have to go this in detail. But essentially, the problem you have to solve is you have these 4 qualities you want to reduce, right? So occupancy, bandwidth, enough computational density. But to statically decide this, again, you have to know what characteristics a certain fusion has. And to make this slightly more complicated, because the Triton question came up, this also depends on how you actually will co-generate this in the end. And when I say co-generation, I also always think of libraries, right? For me, that's a way of doing co-generation. So how do you run this in the end? And that's another problem you have to solve, right? So you have to understand, if I do this fusion, I will run this using this implementation. Like I will run this via Triton, I will run this via cuDNN, and I will get this kind of runtime performance characteristics out of this. And making fusion decisions then kicks you potentially off co-generation paths, right? Because in an ideal world, of course, right, we can co-generate everything. Practically, that never happens. So practically, what we see is that different co-generators have different things they cover. So then if you make a decision, you might just fall off the path, right? Or you make a decision, all of a sudden, your life set of data becomes very large, right? So that's all things you have to understand, and that's why we think you need a cost model, right? Or you need to profile this or something like that. So that's essentially the 2 key areas where XLA GPU is using cost models, or is moving forward to use more cost models in the future.
And quick So this is a case where profiling doesn't really work, because in Fusion you have thousands and thousands of decisions you have to make, like whether to fuse or not, and you can't profile each and every one of them.
Yeah. So that's the two problems we're trying to solve. And that's why we started this open XLA cost model effort that Johannes is very involved in, right? So he is the person to talk to, where we kind of want to make more cost modeling available in XLA GPU. And for the horizontal scaling or like, you know, multi-GPU thing, Rahul would be a good person. So what's the plan, right? So depending on how familiar you are with XLA GPU, but currently in XLA GPU, it's very heuristics based, and it's very phase ordering based in a way, right? So how XLA GPU does this today, solving this fusion problem, essentially there's a first round of passes that pattern matches certain patterns into certain implementations, right? So it will look at convolutions, it will look at multi-headed attention, it will identify softmaxes, it will identify certain map moles that have certain properties, like they have a convert and an input, these kind of things. So it's a fixed set of patterns, and the priority essentially of the pattern is given by the ordering of the passes. So essentially it runs over the graph, and first it does, I don't even know what the order is. I think Triton map mole selection happens very early. So that will eat all the map moles that we think are beneficial for Triton. And then comes the next pass that will see all the MHA patterns that we think is beneficial to do via cuDNN, and we eat them out of the graph. And so we progressively go until we have kind of done this pre-passes. And then we do the instruction fusion pass on the remaining pieces. Like that will be reductions, the element-wise stuff, the broadcasts, right? All the kind of fluff in between. And that's very heuristics-based. Right? So there's just lots of learned things compiler engineers have put in there with a lot of sweat and time to make it do the right decisions. But to be fair, it's not very well understood why our heuristics are the way they are. They just, they work well because they have been tuned for a long time. And then we take another step, which is this fusion merger, which looks at multiple fusions that our heuristics have created, and it tries to merge these fusions into fewer fusions, because fewer fusions means fewer launches, means less overhead. And that actually uses a cost model, a relatively simple one, but it's cost model based. So then we have post-processed the fusions.
Quick question here, merge in which sense? In the cogen sense? Does it basically generate one CUDA kernel or whatever that is? Or
yes, it will turn into one kernel, but this all happens still at the HLO level. So this just takes HLO operations and groups them into something that will be co-generated via a certain path, right? So via a library, via Triton, via our existing LLVM-based emitters, something, right? But it creates these bags of ops in a way. Answer the question?
Yes. Another quick question. Do you guys consider things that for something it's cheaper to actually compute it rather than trying to materialize it?
Yes.
Okay.
But that's another problem that needs solving. Yes. So you might, for instance, fuse a computation into multiple consumers, right? That's what's created this. So that's at the fusion level. We also do this at the graph level later on, but that's a separate problem.
So it's step 3 or sorry, step 2?
I think step 3 does the moving. Which one runs twice? Is it the instruction? I think instruction fusion also runs twice. It first runs with don't duplicate things.
But that's
all details, right? It's all complicated. And then we do other couple of stuff of fusions, right? So the point of the slide is, yes, this works reasonably well, but it's not very principled. It's very hard to understand what it does and why.
Black box.
You can look at it, but it's and it happens to work well in the setup it's right now for the use cases we have right now. But what happens every once in a while is that we have to change like the ordering of the passes, like move the MHA earlier because we want to make sure that they actually get priority over the Triton things and stuff like that, right? So this is not sustainable.
We're also already hitting the limits in some ways. So for example, when you're building the softmax fusions in Triton, you have to decide how much you fuse in there, right? And it's very hard to decide when to stop. So it can happen that you fuse too much and you start interfering with with GPU instruction fusion, and then you end up materializing two big intermediate values.
Is there a reason why MHA is not Triton based?
Well, generally there's no. Well, the ultimate goal is always performance, right? So
yeah,
there's no big reason why something is implemented in some way. It's just so ultimately we want to choose the one that gives you the best performance. That's the goal here.
And I would think Triton is more. I guess you can fuse more things in Triton. It's not it's not like a Cudian and blob. You can only fuse a few things there.
I think part of it is just time. It's a fairly recent development to have Triton.
Okay. Yeah, and then you also have to look at the baseline performance, right? So sometimes Fusion gives you better performance. That's true, but there's another trade-off you have to make, right? So you might also be that like your library-based performance is just a lot better than what you get out of Triton. Right, so it's not like a magic bullet. You just write it in Triton, it will be fast, right? So there's a lot of work that actually needs to happen to make sure it ultimately is fast.
And I guess the difficult thing is you cannot really auto-tune across stages. That's why you guys think about it.
Yes, they're all very local decisions we're making. Right? So the parsers don't know of each other, and that's essentially the key thing that we are trying to solve there is. So if you look at like the North Star, the like super far away limit. So what we really would like to have like a single parse or single framework that does all these decisions in one place. And because it's no longer a local thing, just reasoning about Triton or reasoning about Cudian or reasoning about cuBLAS, that we can actually get to optimal fusions. But it has to, that's the key challenge. It has to arbitrate between different code generation approaches, because assuming everything goes through one thing, like everything becomes Triton, is just not realistic in practice. Right? And also, just to put it in the slide, it's an aspirational goal, right? So it's not like we want to get there, but whether it's actually feasible to do this all in one pass and that will actually work out, that's still to be learned in essence. So what we're doing instead is we do something like a step on this way, so we're doing two kind of things. One is we have to improve our actual cost model. So we have a cost model, but it's sometimes mispredicting. So that's like a work stream we are working on, improving that. And then the other thing is, so if you remember back on the slide, I said we have these multiple steps we're taking. So as a first thing, we want to unify the instruction fusion, that was the heuristics-based fusion thing, and the fusion merger, that was the cost model-based fusion thing, into essentially one fusion system, which is we call it priority-based fusion, and there's an RFC out since I think yesterday, so you can read up on that to kind of get a first step into this unified fusion world. And then I have some pictures just to give you an idea. So this is like cost model improvements. So you can see like the stayers are getting less. Right, so this is active work. So the way we're doing this, we're essentially predicting cost and measuring actual cost, and then we find outliers, and then we look at, okay, why is this different? And this is our analytical cost model that we have an Xlate GPU.
So sorry, very silly question. Does it also include some, I guess, GPU features as well? All right. So it's not just sizes.
So what it does is it looks at the HLO, it looks at the memory intensity, the expected memory bandwidth, the flops, and in this particular before and after example here, one thing that was added on the right was the actual launch grid. So it will basically look at the HLO, say, if I was cogening this, how would I launch it? And then it uses the launch grid to, again, predict the memory bandwidth. If you only have a very low occupancy, you get lower memory bandwidth, right?
So that's one line of work that's currently happening. And then the other one is, as I said, is this priority-based fusion approach. And you can read the RFC, so I don't want to spend all the time on this, but just essentially the idea is you start with your graph of HLO operations, And then for every pair of HLOs, you predict the benefit of fusing them into kind of a fused HLO using this cost model. And that's, as Johannes said, right, that's why you need a fast cost model, because you can't practically profile this for various reasons, right? Just the runtime, but you also have to be able to co-generate all that. So, and once you have essentially this graph now with priority weights, you start fusing the most beneficial priorities, and then build your kind of fused graph that way. And you just keep doing it until you have kind of exhausted all your fusion opportunities. There's some more details to that, right? So you want a certain level of look ahead, maybe, so that you don't, because sometimes you have to like fuse two things to actually get a big benefit.
Yeah, it sounded like it was greedy.
It is kind of priority based, greedy. Yeah.
This is NPI, right? So
Yeah, exactly. Yeah.
So we, this seems to be working reasonably well. We also have experience on the TPU side with a very similar approach. So we have like confidence that this can work. But again, the proof is in the pudding, right? So we have to kind of do this.
Quite there yet.
Yes.
So our goal for this quarter is to get this new fusion algorithm to be on par in terms of runtime performance with the old heuristics-based one, but without all the heuristics. And then hopefully in Q1 and later we can actually get some big wins.
So
I have a question. I was skimming through the RFC, and I thought it said that the global cost model you currently have is only estimating cost for fusion kernels of K-loop type. I was wondering what the challenge is with other types of fusion kernels, like reduction and input fusion and all of those. Is there any technical reason?
It might be a typo in the model in the IFC. Like we also estimate transpose and reduction kernels. We don't estimate Triton or library calls.
So maybe what the RFC meant is originally, before this line of work started, the cost model was only modeling K-loop, the behavior of the K-loop emitters. But since there was a lot of work to actually get this corrected, and kind of also understand this is not actually a loop, but it's a reduction and these kind of things.
Okay, so it does support all of those now. Thanks.
Yeah.
Hello. Hi, Chao from AMD. I just want currently the fusion is based on the instruction levels, kernel level. Is there any plan for the graph, subgraph level fusion?
What does graph or subgraph level fusion mean?
On actual computation level fusion. So right now, if I understand correctly, it's the actual instruction fusion, isn't it? And
But the HLO level, right? So the instruction here is an HLO op. Right?
Yes. For example, there's two actual computations. Would it be possible to fusion this two?
So you fuse two ops, and then you add that fusion back into the set.
Yes.
Of ops.
Yes.
Yes.
Does that make sense?
I couldn't hear. Can you say again, sorry?
Our subgraphs.
So after you fuse two, you identify the highest priority fusion. You fuse that, and then you add that back to the pairs. So you consider its fusion with every other op in the set, and iterate. So you are building up larger and larger fusions as you go.
Okay, so it doesn't matter that it's in different actual computations. That still should okay.
I mean, they have to be contiguous.
So you start with one big graph, right? It's completely unfused. Like not really, but let's just say it's completely unfused. And then you find the producer that has the highest benefit of fusing with all its consumers, and you start with this, and you end up with the number of fusions. And then you repeat the process until there's nothing left to fuse.
Are you talking about like equivalent of inter-procedural fusion, if you will, like across HLO computations?
Yes.
So my question would be, where do they come from? So this assumes that essentially have a computation with a root and then kind of a computational graph from there. So what's the use case of having two computations?
I don't have the currently exact use case right now. I'm just thinking would be more benefits if the fusion is more aggressive. Be more aggressive, not just on the actual instruction level. It's more actual computation level.
Well, I think that we don't have a use case essentially for. We have never looked at that kind of fusion, right? Because essentially we're looking at single computations. But if you have nested computations, they're typically attached to something like a reduction or. So we always assume we have a module with one entry computation, and that's where fusion starts. But it could be an interesting thing. So if there's a use case where we say, okay, I don't know, I actually have two models that I want to mix. But my natural instinct would be that the representation would be a single computation with multiple results, for example. And then you're back to the single computation land, and you can fuse from there. Does that make sense?
Okay, yeah. Thank you. That's my random thought. Yeah. Thank you.
Well, it's an interesting question. Right? So,
I have a follow-up question actually on this one. So we do fusion at HLO level, but I was wondering, are we actually communalizing to like a smaller set? For example, what happens to batch norm? Do we decompose it and then we start doing fusions, or we actually treat batch norms as batch norm, softmax as softmax? So
that's the interesting question. I think batch norm typically in XLA is decomposed, but it's a general problem, right? So how do you want to do this? But that's not. I guess by the time you get to XLA, for me this is like a prior problem, right? So this stable HLO composites kind of world, right? So you come from a framework and you want to preserve the knowledge that this is a softmax, but once you decided to not map it to a specialized implementation, a custom call, a library. I think typically you dissolve it into HLOs.
Okay, right. So we actually start with decompose softmaxes and batch norms. Yeah. I just want to check what this type.
So once you start fusing, right? So
yes,
if it's not decomposed, it would be a custom call because then you have to provide some implementation for this non-decomposed thing.
All right, got it. Yeah. So one of the earlier stages might have latched it to, let's say, QDNM, and then we won't do anything.
Yeah.
Okay.
Or if you have your custom kernel or these things.
Yeah, but long term, we would like all of these things to happen in one pass, as Stefan said earlier.
Mm-hmm.
But there's things like if you use Jax Triton, for example, and if you've written your custom Triton kernel at the framework level, or you have some PyTorch piece that essentially has a fixed implementation, that would just be a custom call. And then there's nothing we can do, right? So it doesn't take part in Fusion because you don't fuse into custom calls.
It's hard, yes.
What are your thoughts about expanding this for horizontal fusion? Anything that is not producer-consumer fusion?
Your thoughts?
For now, it'll probably stay a separate pass. No immediate plans to integrate this.
Well, so when thinking about, I think the problem you have is that you need yet another cost model. Like horizontal fusion is a lot about reducing launch overhead occupancy, right? And I don't think our cost model currently models that at all.
Yeah, we don't model multi-output at all.
And there's like related things. So also fusion decisions we make, right? So how does that interact with latency hiding scheduling, for example? Because we can easily make a fusion decision that creates this super big fusion, but now all of a sudden we reduced concurrency because that's what fusion also always does, right? So once you've fused everything, it's one blob, right? So and especially if you have things like multi-output fusion, right? So this is horizontal fusion. You have the problem that now you kind of tied two independent computations into a single computation, and that takes away your ability to schedule them freely. And you might have, created something that you can't do latency hiding on anymore.
Yeah.
So these are not independent either, right? So
this is a very painful problem. We're running into something similar. So our main fuser is TensorRT, which we're using like kind of as a fuser. But if you run a TensorRT engine, you have to wait until the end before you can, let's say, push some outputs to a GPU. So you cannot hide the latency. So you need to figure out, like, you need to make the fusion smaller so you can start the communication earlier. Like, very hard problem.
Yeah. But yeah, that's there's no plans on how to model horizontal fusion and how to kind of solve this. But it's certainly something that it's very worthwhile thinking about. So it's a problem worth solving. It's just not high enough on our agenda to solve it right now. Instead, I think there's just ways to make it work.
Yeah, I mean, yeah, like I think folks have used optimization barriers and stuff like that to avoid sort of problematic fusions, but yeah, we need a general solution there.
So there's hacks, but there's no answer. So then that would be a great project for somebody to take on.
Also, I'm interested for your cost model to get the estimate runtime. Do you regularly update the estimate runtime, or because right now I think you measure it and you fix, and once a while maybe the library, code library, or they will update as the new feature, the performance improve. I think you need to update the measure number as well. Isn't?
So for libraries, we don't use the cost model right now. So for libraries, we because it's still a pre-pass and it uses like auto-tuning and these things. But once we get to the point that we would also use this fusion approach for libraries, yes, you're right. We need a way to reliably predict performance of these libraries. There's I guess multiple ways to do this, but also for our cost model we do the same, right? So for our code generation cost model, we also remeasure kind of the building blocks to get to the flops on actual devices, and we just measure how far we're off. But yeah, for libraries, that's an interesting question.
Yeah, so that means they didn't have to measure every week or every I don't know what the frequency to make sure that the measurement is correct as possible.
So for libraries, I would expect it's per library update, right? So if the library doesn't change, I would
sure.
change, right? I would expect it kind of stays as it is. But yeah, that's essentially ideally it's a problem that like the hardware, the library suppliers would solve, right? Because they would know what the correct characteristics are.
It's probably a multi-dimensional matrix. It's not just library; it's also hardware.
Yes.
Yes.
Yeah, our cost model knows which GPU it's trying to target. Yes, you need to know that.
Yeah, I guess related to that, like, should we, at some point invest in, targeted tests for the cost model itself? So make sure that their timings are actually correlated, and do that not as a one-off thing, but just like continuously test it at some frequency.
So we added something to the Excel GPU compiler to annotate predicted cost, so that you actually have it in there, and then ideally you should be able to correlate that with something like TensorBoard. But you want to automate this, right? So we also want to run essentially tests, all that, so that you find these outliers. I mean that's essentially how you get to things like this, right? So so you know how far you are off. Because the problem is you just measuring your fusion decisions will tell you this, because you might have made the right decision even though you're kind of very wrong. So that's essentially that. So I think that's just in the interest of time. So that's the other things you brought up. I think you brought up the question of layouts. So we discussed layouts, and the next GPU layouts happens before fusions. So it's like first layout decisions and then fusions, and that's for historical learned reasons. So you could also totally do it the other way around, but you have to pick some order. But you're right, it's not your fusion might totally change which layout you want. So we are aware it's again one of these things that we are trying to not to tackle right now because you can't do everything. But we did some work around, looking at layouts for Triton map models, finding better layouts there. So we're aware it's another area that would be very interesting to understand. But it's also totally not clear to me how this phase ordering problems changes if you fold it into one thing. So if you make a fusion decision and now a different layout would be better, is that always local, or do you then actually?
I don't think it's always local.
But that would be very interesting to understand and kind of.
I mean that's why I was wondering. It's another very hard problem to pick the optimal layouts, like globally optimal, not like greedy approach, but.
Yeah, but as Kai said, we're in his talk, we're very pragmatic. So if it's better on the benchmark suite, then we're happy for now.
You have to start somewhere. So we do global layout optimizations, but we do it independently of Fusion to just make this more manageable.
What measure do we have for how accurate makes sense before the cost model is no longer useful? Like how accurate it needs to be before it's no longer, because like you can model the SM, but like if it's at the bottom of the rack or the top of the rack, it might be running at different temperatures. You'll get 5 or 10% different. Maybe that should hopefully be okay. But how can we measure or bound like how accurate it needs to be?
That's also a good question. So if you look at these graphs, it's not all that accurate right now. I mean, ultimately, if you think about what you want to avoid is like catastrophically wrong decisions. So the problems we typically see is you fuse like a broadcast, and all of a sudden your live set is like 100,000 times as large as before. That's something you definitely don't want to do. Or you fuse something and you fall off a code generation path. That's also something you don't want to do. So these are the easy ones. I don't know. I think we have yet to see how much other things we find where like 5, 10, 20, 30% will make a difference. I don't know this right now. Do you have an answer, like how accurate it needs to be?
So with the current model, we're within a few percent of the old Fusion, the heuristics-based Fusion pass. So we think we need to be a bit more accurate than we are right now. I don't think you need to be super exact. Like if you model things like coalesced reads, as Stefan said, like whether you're still on the happy path of code gen, I think you can probably get to a decent state. Probably not state of the art, but very decent. And this is a lot about performance on like out of the box performance on models that weren't tuned, right? XLA GPU has really good performance on the models that it was specifically tuned for, but on like random models, it's could be better, and this should help.
And I think my intuition is also more like the compute is less critical than is like memory bandwidth. Right, so they coalesce reads. So if you can predict things like, okay, this is coalesced, this is not coalesced, I think that in my intuition is more important than kind of figuring out the last little bit of how effective this is in computing. So that's why I mean our flops model is fairly inaccurate. So
and also like if you're turning a read into an uncoalesced read, like this is so catastrophic that even a really inaccurate model will still, like if you're wasting 90% of your memory bandwidth, then it doesn't really matter if you're off by 10% otherwise.
And also for as you mentioned, like the temperature in the rack and these kind of things. I guess for fusion decisions, I don't think that's critical, because you have to make fusion decisions anyway for like
right,
no matter how this is running, right? Because also for things that matter, your GPUs are running in different places of the rack, right? We typically don't run a model on one GPU in one place, right?
I mean, this is where layouts come in place. You can transpose to get coalesced reads, and sometimes it's the right thing to do.
But that's why we have this global layout analysis, that it transposes. The idea essentially is like the intuition is that layouts are dominated by the operations that matter, right? So like a map mall, right? So that has a layout constraint. So that's how layout assignment works. So for certain operations where it matters, like convolutions, map malls, you get these constraints, and then we try to propagate them to avoid unnecessary transposes. That's basically the approach that currently exists. And the intuition is that this is independent of fusion. So once you've found the right kind of layouts, essentially, even if you fuse, it should stay fine. I think where this breaks down is if the transpose is in the wrong places or things like that. But roughly, it worked very well for what we needed.
Actually, another silly question. Does this like is scheduling in scope basically pushing, let's say, transposes a little bit earlier or like closer to producers or consumers?
It happens elsewhere.
Yeah. But it's an interesting question. Should we move transposes in different places so that we can do better fusions? But I think what happens in practice is if you can push a transpose somewhere, we typically also can fuse what's in between, because we push transposes over things that are kind of trivial, and then it doesn't impact fusion for practical purposes.
Mm-hmm.
But again, this is more like, so far, and you never know. But that's why this is also still a separate thing, essentially. But it's also constantly happening. But in the interest of time, because we also have these other things on our agenda. So how do you get cost models, right? So that's the other big question, the kind of elephant in the room. So do we do it analytical, profile-based? How do we do OpenAI Triton? So that's all, open questions. So I think what we do know is profile-based is too expensive for our use cases, because we need to use this during fusion formation, and that would mean we would have to profile a lot of fusion candidates to make this worthwhile. I mean, that essentially, it might work for something like, at Google scale, where you can build up a database, and because we run so many workloads. But in general, for other kind of places, it just doesn't scale in that sense. So that's where, offline analytical cost model based is a lot easier and preferable. And the other reason is because it allows you to actually compile on the device that doesn't actually have a GPU, right? So that's also one of the big goals we have long term, because you don't want to spend your kind of expensive GPUs idling while you're compiling code, right? So ideally, you want to compile code somewhere on a machine without a GPU and only ship it to GPUs once you want to start computing. So that's why we think analytical is the better way. Or offline learned. I don't know where that question came from, but essentially, yes, if you can learn a cost model, that would also satisfy our kind of offline requirement.
But it'll probably be a mix, right, of offline and online. So some auto-tuning for certain parameters, but more like tile sizes, for example.
Unless somebody writes a good way to predict tile sizes, so we don't have done. Auto-tuning is typically something you do because you don't have a better answer. It's kind of the big hammer that always works, but it's costly, right? So ideally, we wouldn't.
You do need a device.
Yes. So the nice, future North Star, if we had all the engineering and answers on the planet, we wouldn't do any auto-tuning. We would all be analytical or learned or whatever. But in the meantime, for practical reasons, yes, we do auto-tune in places. That's true. So how to cost model OpenAI Triton. So that's so it's just somebody has to build the cost model. I think it's not fundamentally different to how we cost model HLO, right? So in essence, you have an IR and you know what the compiler will do, and then you could predict what performance it has. So it's something that would need to be built.
I think the most likely thing that we at Google will do is to cost model this at the HLO level, just like everything else, and encode the Triton specifics in the model. But it'll be pretty coarse for now. So we're not doing any fine-grained Triton modeling.
So
You would need to understand you would need to understand to some extent what the Triton compiler would generate, or would it? That's the tricky part, right?
So we expect that a coarse model will be good enough for now. Again, we're being pragmatic about this. The current way we build these Triton fusions has no cost modeling at all. So basically, anything will be a step up from that.
So you take the HLO that happened before fusion.
No, during
Or-
fusion, like you can
Sure.
look at the HLO,
Okay.
and I mean,
And you just assume
how
that
much
don't need
data it
to-
will be.
You'd assume you don't need to rematerialize or write out to memory any of the
Any of
things
the
between
intermediates,
ops,
yes,
intermediates.
yes,
So you'd basically just use feed the plot model off of.
most likely. Yeah.
That, and any inputs and
This will be
outputs.
the first iteration, right? So probably assume reads are coalesced and otherwise use the default.
But to
We'll see.
Jaya's point, yeah, you have to predict whether the Triton compiler will get coalescing working, right? So there's some prediction that you have to do, but also the use of Triton is it's not like a full-blown use of Triton. So we don't have like arbitrary Triton kernel next to the GPU. It's used in limited places. So it can be a mapmol with input-output fusion, or it can be a softmax, right? So these things are, I think, reasonably predictable what the Triton compiler will do with them.
Mm-hmm.
But if you want to do this in the full generality, right? So if you would allow people, if you would have like arbitrary Triton, then that would be a lot harder.
I'm not saying we'll never do this. Just for now, like we just got to get the basics working.
What else did we have on our list? Extensibility for custom ops.
I can take this one too. Like our thinking here is that we'll, I think Kai also alluded to this in his talk, that we'll have this, what do you call it, kernel provider?
That was the term that was thrown out.
Yeah, kernel provider interface. So basically, it could be a library, it could be Triton, it could be legacy emitters. And what these things will have to provide is a way to predict the cost of a fusion, or like to say, though, I can't cogen this at all, and a way to actually cogen it. And the first one would be used in the fusion pass. So basically, the fusion pass just produces these proposed fusions. It asks all of its providers, "What do you think about this?" and picks the best one. If there is one that says the fusion will be better than both individual ones. I hope that made sense.
Do you have some rough idea what API contract will be there? Because it will be costly to change later on.
Yes. So we are not in the design phase for this yet. We are pretty close to having agreement with all the relevant people about the fact that this should happen, but design phase is not yet started, and there will be RFCs.
Which will be the key time to kind of chime in and make sure it
Yeah.
also works for your use case. Right? So the eternal discussion is about like, is this something to invest in right now? Is this something we need right now? Right. But then the question, how do we design this? That's ideally feedback based, because it has to work for various use cases.
But I expect we will start with a fairly small interface. It won't be huge, like a few functions.
So we have 5 minutes left. One thing I also would like to get out of this is like, how can we kind of collaborate on this? What's the interest in this? What are different people kind of wanting to do in cost modeling? But is there some way we can make it easier to jointly work on this, or any feedback there? Like, how do we make this actionable? Right, so that's essentially the other thing.
I think one open question I have is that you mentioned that the GPU cost model is not accurate at the moment, or it could be made more accurate. So if that is something we can collaborate on and help you with, you can define to us what kind of inaccuracies you see and what level of information you need
Yeah,
from
we
GPU backends.
yeah, we want to participate in this part as well. And the GPU want to know what kind of materials you want to know.
Yeah, I think we have a long list of stuff that could be done. Maybe we just have to get it out there on GitHub somewhere. That's a good point.
Okay, that sounds like some action item we can take right away.
Yep.
Yeah, especially making this work on kind of AMD GPU hardware, that would be much appreciated to get help there, because that's it needs evaluation, like creating these graphs and just understanding where the model is, and that's a lot easier if you have access to all the different hardware. So that would help. Anything else? Any feedback on things we could do?
Do we need to define a set of machine parameters, like latencies, and I mean, we already have bandwidth and things like that, but there's also, like, I think internode things get very interesting with communication. You have to potentially derate your network bandwidth because the nominal rate isn't always accurate, and different hardware providers get different percentages of peak that you might expect. Whether the network is contended, how many switches you might have to hop across, like there's, how is the user going to specify, especially in an offline case where you can't just go and query the machine that you're running on, how is the user going to specify like enough about the machine that you can then go and actually model analytically what the performance is going to be for some collective that might be cutting through one dimension or another dimension.
Like defining the topology.
So you need the mesh, but you need, like, yeah. So is there going to be like a collection tool for that? What would be the metrics that we're going to need for the model? I think there's a discussion there that has to sort of happen to, like, we can go off and try to build the model for that. But what parameters are you going to give us in order to try to fit it, so to speak?
Yeah, I mean, there's, yeah, like to what degree we can parameterize the cost model. That was one thing, and I think in the past there has been suggestions of having stock cost models for popular setups, if you will. So that's, I guess, just a way to have inbuilt parameters. But yeah, I guess the starting point is to have a cost model that can be parameterized and still is sufficiently accurate for what.
I think they mentioned, you guys mentioned about benchmark infrastructure before. I think that could be a starting point, maybe, because we can compare with that kind of things. In that, I think because the way the fusion, the way affect the benchmark infrastructure, that have the results come out in the benchmark infrastructure, the way run or different models, something like this.
So can you repeat the suggestion? I'm not sure.
I think he's just saying that we could work together to build the benchmarking infrastructure. Like that could be a task that someone takes.
Yeah.
Yeah, I think there's RFC. They mentioned that there's a benchmark structure that we can happen, and then we can measure we can build the cost model based on that to do to measure all the fusion decision or the hard GPU metrics, something like this. I just think I just think this could be one of the options. Maybe there's other bets. I don't know. Sorry, I haven't.
You're talking about learning a cost model based on the benchmarks?
Because we need something to measure whether there's you just mentioned to get the accuracy. Things we need to know all the infrastructure things. So we need to have some benchmark infrastructure things.
Yeah, I think there's two parts to this. So one is like measuring the accuracy of your cost model, like creating the graphs that are still being shared here. And yeah, that requires a benchmark set. I think this ran over our internal benchmarks.
Yes.
So, but that's something that's happening as part of OpenXL anyway. That we have an externally agreed upon, benchmarking set. And at the end of the day, it doesn't really matter all that much what your specific benchmarks are for tuning your cost model, as long as they cover like a broad range of potential as you code generate. But you're right, and the other aspect is that you want to be able to measure whether your fusion decisions are good. And my hope is that they are kind of separate to some degree, right? So one is a question for the general approach. So I guess if our priority-based fusion works well, assuming a tuned cost model, then the hope will be that independent of the architecture, it's going to work. But yeah, we have to work together to essentially enable others to create these graphs that we're sharing here. So maybe that's another action item to explain how we produce them and how that works. Because the pieces are there, right? You just have to tell people.
Yes. But we don't. It's an open question how accurate the model actually has to be. We don't. As you said earlier, it's mostly about preventing the catastrophic decisions.
Yeah, like even on the scheduling side, like that's an open question. Like, how much accuracy do we really need to get good performance? I mean, after some point, it's probably not worth improving the accuracy.
Regarding scheduling, I think we probably need to integrate cost model with the scheduler, like for scheduling aware cost model, because we overlap a bunch of operations all together, and it's going to change the cost quite a bit. Like communication kernels take up SMs, and then you won't be able to have SMs for compute kernels or vice versa. So
Or does that need to become a sort of horizontal fusion?
Yeah, maybe it could be.
Cost model.
Yes.
yeah,
That's
just implemented differently, not like a separate single kernel, but
yeah.
Two streams.
that goes into occupancy again, right? So that's which we're not modulating, right?
Yeah.
So but you're doing multiple things on the GPU in that sense, right? So that's another one where, but again, I because we do these things at different stages of compilation, right? So it's very hard to reason about them globally, right? So that's something that I guess makes sense, but I don't think we have an answer at all how to get there, and whether it's because it's not the most burning problem in a way, right? So because there's like optimization barriers and stuff you can put in to prevent catastrophic wrong decisions, but otherwise the inaccuracy so far seems not to be bad enough in a way, right? Like
And for the latency ideal scheduler, yes. I mean, right now we don't have a cost model, so we are relying on profile guided. So, we are starting to put something together. Like TJ is working on that. I think it remains to be seen if that's can be evolved into something that is good enough, and hopefully we can deprecate profile guided, or do we still need to keep? I think that's only time will tell.
Yeah. So that's why I try to keep all these things separate, right? So yes, we're aware that they are inaccuracies. Jesus, difficult word. But and I have the jet lag excuse. And then so let's try to solve the simple separate problems. But that's the long tail, right? So all this occupancy, horizontal fusion problems, they are lurking there. But we should be aware, but not now. I think that's the
maybe there are second order effects as opposed to modeling memory bandwidth and those kind of things to the first order.
Yes. We had them on a list when we thought about this. They just fell off the plan because
Taking a breath first approach.
I think we are out of time. If I remember no.
5 p.m.
So we're preventing you from getting to the important session. But any last thoughts? Anything we should take away? Also from the online audience.
Question. So for the workloads you benchmarked on, how much end-to-end speed up did you see migrating to the new cost model based fusion?
Yeah, so it's as I said earlier, we're currently mostly trying to reach parity with the old pass. On some workloads, we are seeing decent improvements. On others, we're still a little bit behind. So it's currently overall we're in the mean, we're slightly behind the heuristics-based approach still. But we're fairly confident that we can catch up this quarter.
So the gaps, so you think mostly by improving the cost model accuracy, you might get there, or?
So we have some very crude modeling for coalescing, for example, and we believe that improving this will give us a nice boost. Then we know that, for example, the caching model is extremely crude so far. It assumes each parameter gets to use the entire cache, for example.
Do you know when to stop improving the cost model and switch to the second, of basically improving the priority fusion?
It's basically the same thing. The priority fusion algorithm is very simple. So it's essentially all the smarts is in the model.
Okay.
And so for now, we're improving this until we reach parity, and then we'll ship it. And then the next step will be to include Triton. Like, this is where we expect that we'll have big performance wins. Because again, like the fusion algorithm for Triton is very crude right now.
So including Triton is like the first time we take these pre-passes that we had, right? Step one, where you pre-pattern match pieces and integrate that into the overall fusion passes. And that will help, because we then don't make like local decisions anymore, where we know that we ideally would want to make some fusions, but don't, because we have to be conservative with our local reasoning. Right? So that's where the big benefits will come. And the long tail. Because keep in mind, XLA GPU is very well optimized for the workloads we care about, naturally. Right? So the heuristics work fine for those. And we will keep improving them to work fine, because it has to stay fast. But we want to switch to this cost model so that we don't have to do this anymore, and that we can have this more global view. So that's more the right way to think about this.
Thanks.
Okay, so we have a little list of things we can do to make this more easy to engage in. So we'll work on that. And yeah, let's keep the conversation going. And
are you guys thinking of like scheduling just monthly updating or something like that?
Good idea.
so there's the monthly OpenXLA community meeting, I think. And we could just give an update on progress on Cosmos there. That could be worthwhile. And if that doesn't kind of scale, right? So if we need more time, then we can go to separate meetings, I think. So that's good feedback.
Sounds good. Thanks, everyone.
Thank you.
Thank you.